All right, you guys, today we're going to continue with projectile motion. Now, the first thing that's important about this is that a projectile is an object that moves in 2 dimensions. So since we talked about 2D kinematics yesterday and 2D motion, what it is a projectile. And it's only under the influence of gravity. So you know how when we did free fall, it was only under the influence of gravity. So when I dropped it, only gravity acted on it. Well, it's the same thing with the projectile, except for now, instead of just falling straight down, it would be like I took this and I tossed it. Now it's a projectile. And the only force that's acting on this after I let go of it is gravity. Of course, when I throw it, it's going to have some sort of initial velocity, but over time, all that's acting on it is gravity. So we are going to continue to neglect air resistance for now. We don't care about it. It doesn't matter. So the other thing just to cover before we get into this is that projectile motions in 2 dimensions are going to follow a parabolic trajectory. Okay, so here we have an example of what a trajectory would look like. We have our x-axis, we have our y-axis. This would be our object, and we would throw it with some v0, some initial velocity, okay? And that v0 would be broken up into components, like we've talked about previously with component vectors. There is going to be an x component of velocity and a y component of velocity. Now, when you throw it with this velocity, it's also going to have an angle theta. We need to use that angle when finding our x and y components of the velocity. So v0 x is going to be equal to v0 cosine of theta. And then our v0 y is going to be equal to v0 sine of theta. Okay? This right here, this theta has a name, and it is referred to as the launch angle. So if we're doing a problem and I tell you that the launch angle is 30 degrees or something like that, it's referring to this theta right here. That's going to be our launch angle. Now, the other thing to think about is that I said that the only thing acting on this object after we throw it is gravity, okay? That means nothing else is acting on it, which means there's no forces acting on it in the x direction. So that means that our acceleration in the x direction for trajectories or projectile motion is going to be equal to 0 meters per second squared. So that means whatever this initial x velocity you find is, that is going to be the x velocity of this object the entire time it is going, okay? Now, what will change is we will have a y acceleration. Now, if the only thing acting on this object is gravity, the acceleration in the y direction is going to be negative g, which is negative 9.8 meters per second squared. So what we can take from this is that an object that's projectile motion is actually just an object in free fall, like we've been discussing previously, okay? So no acceleration in the x direction, negative g acceleration in the y direction. And that makes sense because of course there's going to have to be some sort of acceleration in the y direction because what goes up must come down, okay? Which means there has to be something acting on it in that y direction to get it to come back down. Now, you might be wondering, if this is what the velocity looks at the beginning, what's it going to look like at other places? Well, the velocity is always going to be tangent to the curve, okay? So the velocity will always be tangent to our curve. And then on top of that, our acceleration is always going to be acting downwards. It is always just going to be straight down. And the arrows will always be the same length because the acceleration is going to be the same at every single point, just like it was when we were doing free fall, okay? The acceleration is the same at every point. So just one more time, take this home. Projectiles are in free fall. There is no acceleration in the x direction. There's only acceleration in the y direction, and that acceleration in the y direction is negative g. All right, so let's do an example together. All right, this example is called Don't Try This at Home, but honestly, don't try it anywhere, okay? So a stuntman is driving a car off of a 10-meter high cliff, okay? So that's gonna be 10 meters at a speed of 20 meters per second. So if he's driving off, that means he was going 20 meters per second in this direction, okay? Going 20 meters per second off of it. How far does the car land from the base of the cliff? So we want to know where the car is here. That's what we're concerned with. So let's start out by listing out our known values. Okay, so one of the first things that we know is our initial x position is at 0 meters. We also know that our initial y position is at 10 meters. Okay, what about our velocities? Well, he's going in the x direction as he drives off the cliff. So our initial velocity in the x direction is going to be 20 meters per second, but you'll notice there's no y component here. So his initial velocity in the y direction is going to be 0 meters per second. We also know that this is a parabolic trajectory, right? So that means that this is a projectile. So our acceleration in the x direction is going to be 0 meters per second squared, and our acceleration in the y direction is going to be negative 9.8 meters per second squared. Now, that's everything that we know, and what we want to find is what xf is equal to. How many meters has he gone in the horizontal direction when he lands? So let's look at our equations. We're going to look at our xf and yf equations. Okay, so the first thing we're going to want to do with these equations is we're going to want to go through and we're going to mark what we know is 0. So our x naught is 0, our ax is 0, our b naught y is 0, and our yf is going to be 0. So that means that our equations now are xf equals v naught x t, and our yf would be 0 equals y naught plus 1/2 ay t squared. From here, we can solve for the time it takes for this car to reach that final position. How we're going to solve for that is using our y equation, because we have all of these values and all we don't have is that t. So we subtract y naught from both sides, multiply by 2 on both sides, divide by ay, and then take the square root. Okay? So when we plug this in, we're going to have the square root of negative 2 times 10 divided by negative 9.8. You take a second and you plug that into your calculator, you're going to get 1.43 seconds. So it's going to take 1.43 seconds for this car to get to its final position. Now that we have the time, we can plug that in to this equation in order to find our final x position. So what we're going to do is we're going to take our initial x velocity of 20 meters per second and multiply it by this time we found of 1.43 seconds. So if you do 20 meters per second times 1.43 seconds, you're going to find that the car has traveled a total horizontal distance of 28.60 meters. So that's our final answer, 28.60 meters. Okay, let's do one more example together. Then I'm going to leave you with a problem to try and work out before you come to class tomorrow. Okay, so frogs have pretty long, strong legs, right? They are excellent jumpers. And there's actually a place that has jumping frog contests every single year in honor of a Mark Twain story. So we have extremely good data on sort of how far frogs can actually jump. So high-speed cameras at this festival show that a good jumper goes into a crouch, okay? And then once he gets into a crouch, he rapidly extends his legs and he jumps up, typically about 15 centimeters during a 65 millisecond push-off, leaving the ground at a 30-degree angle. So we want to know, how far does this frog leap? So this is sort of what his trajectory would look like. And we need to list out some knowns and unknowns, okay? Now we're gonna have two sets of known values. We're gonna have the ones where he's pushing off, and then we're gonna have the ones when he's actually in flight, okay? So his knowns for when he is pushing off. We know that he's going to start at an x naught of 0 meters and a y naught of 0 meters. His x velocity initially is going to be 0 meters per second. His initial time is 0 seconds. And then his final x position is going to be 0.15 meters, and his final time is going to be 0.065 seconds, okay? That's sort of everything that we have been given. Something that we need to find, though, is what his final x velocity is, because that'll tell us how fast he's going when he actually jumps. So let's start with finding that, okay? So push off. If we want to find this final x velocity, first we are going to want to break down the xf equation in order to solve for acceleration, because VF equals V naught plus AT, and we don't have an acceleration yet. So if we go and we do XF equals X naught plus V naught XT plus 1/2 AXT squared, we're going to know that X naught is 0. We know that V naught is 0. And we can say XF equals 1/2 AXT squared. And now we just need to solve for that AX, which means we'll multiply both sides by 2 to get 2XF equals AXT squared, and then divide both sides by T squared. Now that we've got it there, we have all the values we need to plug it in. So we're going to have 2 times our XF of 0.15 meters divided by our time of 0.065 seconds squared. Now, if you take a moment and type that into your calculator, you're going to get around 71 meters per second squared as our acceleration. Now that we have that acceleration, we can plug it into our VF equation. So we can take VFX equals V naught x plus AXT, right? We can get rid of that because we know it's 0. And we're going to get that VFX is equal to 71 meters per second squared times our time of 0.065 seconds. And when we take the time to do that, we are going to get a final velocity of 4.62 meters per second. Okay, 4.62 meters per second. Now you'll notice we have an acceleration in the x direction. Don't get confused. That's because this is the frog pushing off. He's not in projectile yet. He's not doing the trajectory yet. He's just getting ready to push off to then jump forward. So now that we have this information, this is basically going to be our initial velocity for this frog. So we need to talk about him in flight. So if we list out our knowns for this frog while he's in flight, we're going to know that we're going to say that he starts at 0 meters for x and y to make the math easier on us. We want to know what his final x position is. We know that when he lands, his final y position is once again going to be 0 meters. We know that once he's in trajectory, his x acceleration is going to be 0 meters per second squared. And we know that his y acceleration will be negative 9.8 meters per second squared. So remember, what we're looking for is that xf. But first, we are going to need to break this velocity up into components. Because remember, the other thing we know is what we just found, which is that V naught equals 4.62 meters per second, okay? And that's the magnitude of this vector right here. So what we need to do first is we need to break this up into its x and y components of V naught. Thankfully, we were told at the beginning that this launch angle is 30 degrees. So to find our x component, we're going to do 4.62 cosine of 30. And to find our y, we'll do 4.62 sine of 30. So that means that our V naught x is going to be equal to 4.00 meters per second, and our V naught y is going to be equal to 2.31 meters per second. So now we need to do the same thing we just did previously, where we looked at a position equation, okay? But this time we're going to do it for x and y. So now that we've got our equations, the first thing we need to do is cross out whatever we know is going to be 0. We know that there's no acceleration in the x direction, so that's 0. We don't have an initial position for either x or y, they're both 0. And we know that when the frog lands, his final position is going to be 0. So what we're going to get here is that xf equals v naught xt, and that 0 equals v naught yt plus 1/2 ayt squared. Those are going to be our two equations here. Now, what we're asked to find is that final position. So we need to figure out what our time is going to be. And we can do that by solving for the time here. So we're going to want to factor out a t. We're going to get 0 equals t v naught y plus 1/2 a y t. Okay, and we're going to get 2 results for our time. The first result is going to be when t equals 0, yf is 0. And that's true because that's at the beginning of our trajectory, but we don't want that one. What we want is to find this t over here. So what we're going to do is we'll divide both sides by t, which will get rid of that t, and we'll be left with 0 equals v naught y plus 1/2 a y t. Now, we take this, we're going to subtract v naught y from both sides to get that t term by itself over there. So we're going to end up with -2 v naught y divided by ay equals t. When we go back, we can now plug all of our values in, and we're going to get -2 times our v naught y that we just found divided by our ay, which is -9.8 meters per second squared. So we have -2 times 2.31 meters per second divided by -9.8 meters per second squared. And that is going to give us a time of 0.47 seconds. Okay, now that we have that time, we can take it and we can plug it into our equation up here. So we are going to have 4 times 0.47 because our initial x velocity was 4 meters per second. Our time that we found was 0.47 seconds, and that's going to give us a final position of 1.88 meters. Now, if you want to see how to do this just by completely plugging in all the variables and then just getting to the end result without finding the numerical values first, that is done on the PDF of your notes. But I decided to just go ahead and go through and show you how to do it step by step by finding all the different variables to then plug in. Now you get left with a question to try out. So a ball thrown horizontally at 25 meters per second travels a horizontal distance of 50 meters before hitting the ground. From what height was the ball thrown? So I need you to find why not. And I will see you tomorrow.